Hello, this is part of chapter 2.2, example 4, and you'll see we're asked, when does the derivative exist? So the process of finding the derivative is called differentiation, and a function is said to be differentiable at a if the derivative exists at a. And you'll notice here it says it is differentiable on an open interval if it's differentiable at every number in that interval. So let's take a look at example 4, and let's explain why this example is not differentiable. We have the function of the absolute value, so let's use. So here we're going to use the definition of the derivative, and I'm going to pause the video and just write this out. So I just plug this into the definition of the derivative, and I'm going to keep solving this. Which will give us this. All right, now let's look at this for a second. Remember, in order for the derivative to exist, or the limit to exist at 0, the right-hand limit and the left-hand limit must both equal each other, yes? So let's take a look at our left-hand limit. I wrote the left-hand limit in red. Now please look, if we are approaching 0 from the left side, that means from the negative numbers, we're going to have this. And negative h over h is going to be negative 1. So our left-hand limit is negative 1. Let's now take a look at our right-hand limit. And I have that written in green. So notice if we're approaching 0 from the right side, that means we have all positive numbers, yes? So we're going to have h over h, which gives us the limit of 1, which equals positive 1. And if you notice here, our left-hand limit and our right-hand limit do not equal each other. So therefore, the limit does not exist here, which means our derivative isn't going to exist at this particular point. And one way we can think about this, if you were to actually look at the graph of absolute value, it would be some sort of a V, right? Let me just quickly draw an axis in here for you. So let's just pretend this is a beautiful graph at x equals 0. Notice we have a corner there. And graphically, when we look, we'll know the derivative is not going to exist at a corner, which brings us down to the next example. So let's take a look at graphs when the derivative may not exist. If your graph at A has a corner, our derivative will not exist there. If our graph has a hole, that means it's not continuous at A, then it wouldn't be differentiable at A either. And lastly, let's say at A, our derivative, let me see if I can draw this nicely for you, but let's say the slope at that certain point is a tangent line. Tangent lines have slopes that do not exist, correct? So that means the derivative won't exist either. Let's take a look at the theorem at the bottom. If f is differentiable at A, then f will also be continuous at A. Let's take a look at example 5 here, and we want to know where the values are. F is not differentiable. Let's look. We have a hole right here. It looks like at -1. So our function is discontinuous there. There's a hole. And also notice at x equals 2, we have a corner. All right, so at x equals 2, f is not differentiable because of the corner. Now, we will have higher derivatives. Not only do we have the first derivative that oftentimes we show like this, or sometimes like this, we also have higher derivatives. Like we can take the second derivative, which would be shown maybe like that. We can take the third derivative, which might be shown like this. So for a moment, this example 6 asks us to find the second and third derivative. I'm just going to find the second one. And then in order to find the third, you take the derivative of the second derivative. But let's go ahead and do this. So if we go back to example 1 in 2.2, we already found the first derivative for this equation. If we are asked to find the second derivative, all we have to do is take the derivative of the first derivative. So I'm going to go ahead and pause the video, and I'm going to write down the definition of our derivative again. There we go. That is our definition. Go ahead and pause the video if you need to. Now I'm going to substitute from above. And so we'll have that. From here, I'm going to go ahead, distribute the negative. I'm going to expand that x plus h squared. So after I expanded my x plus h squared and distributed by 3, and then I distributed by the negative in front of the parentheses, I got that. Notice a few things may cancel for us here. The -3, +3, -3x squared, +3x squared. And so we're going to be left with this so far. Okay, from here, we're going to go ahead and factor out that h. And we're left with the limit as h goes to 0 of 6x plus 3h. We can substitute in. That's 0 now, and we'll get 6x. So this means our second derivative is 6x. You do the same for the third derivative, but you'd plug the second derivative into the equation. Okay, and that is our video from example 4, 5, and 6.